Yeah. All right, thank you. I see people are settling back in with their coffee. All right, so I am going to talk about how stuff in Galaxies gets arranged. All right, so I know this is a mostly cosmology meeting, and at cosmology meetings, Galaxies are often approximated as, it's not a cosmology meeting, Sandy's shaking her head at me, it's a Galaxies meeting. It's an extra, it all looks the same to me. Remember, I started my career working on things that are, less than a kiloparsec away. All right, so it's far. And people who think about far tend to regard Galaxies as points. So the theme of this talk is that Galaxies are not in fact points, and we should maybe pay a little bit of attention to that. All right, I should mention, most of the work I'm going to show is not my own. It is the work of others, and in particular, 3 graduate students, 2 of whom are probably known to most of you. Nathan Goldbaum, who just recently defended, hooray. John, who you heard from earlier in the week, and Antoine Petit, who is a visiting student from France here a few years ago. All right, so here's the outline of the talk. So I want to start with what we know about the radial distribution of gas, star formation, and metals in Galaxies in the local universe, because that's really the thing I want to focus on trying to make sense of. How did Galaxies get into their current shapes? Then I'll talk about how stuff gets moved around in Galaxies, and I'll focus on, in galactic disks, the transport of mass and metals. I'll talk a little bit about what happens at the very centers of Galaxies, and then I will summarize for those who have fallen asleep. All right, so slight lag there. Let's talk about, well, how is gas arranged in Galaxies in the local universe? So in disks in the local universe, turns out gas is distributed in an approximately exponential distribution. All right, so here's total gas surface density versus radius, and you can normalize things to R25, and you see you wind up with this fairly universal exponential profile. All right, now, most of the gas inside, about half of R25, so inside here is molecular. Most of the gas further out is H1. All right, so there seems to be this fairly universal profile. The scale length is about half of R25, and again, inside half of R25, most of the gas is molecular. Outside, it's not. We'll see a few Galaxies, including our own Milky Way, have central dips, have a gas surface density distribution that goes down in the center. That's a sort of 10% effect. About 10% of the population has a central hole for L-star Galaxies today. The other thing I want you to notice is that the H1 distribution is extremely extended. All right, this plot stops at 20 kpc, but in fact you can detect it significantly further out. You can routinely detect 21 centimeter emission 30 kpc from the center of a galaxy. All right, so the H1 disks of Galaxies are very extended compared to their stellar disks. And as you go further and further out, you just get more and more gas rich. All right, so how about the star formation? How's that arranged? Well, we've heard this several times. In the centers of Galaxies, the H2 depletion time is roughly constant. It's a few gig years. All right, and star formation just sort of follows H2. All right, so what that means is that since most of the H2 is inside half of R25, that's where most of the star formation is too. All right, the star formation distribution more or less just follows the H2 distribution. All right, so star formation is more centrally concentrated than total gas because it's following the H2 and not the H1, which is, again, more centrally concentrated than all the gas put together. All right, and so here's a plot of that depletion time versus orbital time as a proxy for distance from galactic center from Adam Leroy's most recent paper. And you see, again, a constant depletion time, sort of independent of where you are in the galaxy, in the molecular gas. All right, so star formation just follows the molecular gas. Now, this means that some Galaxies do have star formation quenched in their centers. It's more or less the same proportion that are missing gas in their galactic centers. If you've got gas, it'll generally tend to be star forming in the center of a galaxy. If you want to quench the center, the way you do that is you get rid of all the gas. All right, but there's a slight complication on top of that. If you look a little more carefully, you do find something interesting going on in galactic centers. All right, so here is a ratio of the depletion time to the mean depletion time as a function of galactocentric radius. And so you see in the outer parts of disks, not surprisingly, this is flat. This is just a ratio of depletion time to the average of depletion time. It should be about flat. But in the innermost parts of galaxies within the central sort of 1 kpec, you see that, in fact, the mean of these blue and green points is a little lower. All right, there's a very wide dispersion, but roughly speaking, what you see is that sort of a third of galaxies have normal depletion times in their galactic centers, and about 2/3 have shorter depletion times, which means they form stars a little more rapidly in their centers. Not a huge effect, sort of a third of a dex, but it's detectable. All right, so that's how star formation is arranged in galaxies. So this is a problem, and here's why it's a problem. All right, in order to supply that star formation in a typical L-star galaxy today, you need about a solar mass per year, just because that's the rate at which gas is forming stars. All right, here's a plot of the Schechter function for star formation rate in the local universe, and you see that it's sort of, order of solar mass, a few solar masses per year is the L-star for star formation. All right, now, inside R25, the time to consume your available gas supply is much less than the Hubble time. That's true at z of 0. We heard from Linda that it's true at high z also. And I'm just illustrating this here. Here is the depletion time, or the inverse depletion time, as a function of galactocentric radius. And this dashed line I've drawn here is where the depletion time equals the Hubble time. So everywhere inside about R25, the depletion time is much less than the Hubble time. So you'll use up all your available gas supply in less than a Hubble time. And here's where we have a conundrum. The conundrum is, all right, well, most galaxies aren't quenched in the center. All right, only maybe 10% are. So we can't run out of gas in the centers. All right, and we have to be resupplied much more quickly than the Hubble time. All right, but the problem is, this requires that the gas supply be delivered to where the star formation is taking place, which is much more concentrated than the total gas. So we have a mismatch. You have cosmological accretion. We expect that. That's totally fine. The problem is, cosmological accretion should mostly be occurring at large galactocentric radii. But where we need the gas to keep the star formation going is at small radii. It's in the centers of galaxies. So somehow we have to get the mass from the outside to the inside. All right, now you can partly offset this problem by recycling material from old stellar populations. That'll help. But it seems unlikely that that can solve the entire problem for reasons of metallicity and for a variety of other reasons, including the fact that if you were solely burning resupplied fuel, then you should have no deuterium left in the centers of galaxies, for example, because that should all get destroyed, and that's not what we observe. All right, so this is the problem. There's a related problem, which is the metals. All right, so you can ask, suppose that I think gas sort of stays where it lands. All right, suppose I think that there's no moving of gas in galactocentric radius within galaxies, and the same for stars. What should the metallicity distribution look like? All right, and you can say, well, all right, let me take two simple chemical evolution models. All right, two extremes. I can take a closed box or an accreting box. And in either one, the metallicity is equal to the yield. That's just something that depends on the IMF and nucleosynthesis, and the gas fraction. All right, and it turns out these two different functions you get look more or less the same when the gas fraction is near unity, which it is in the outer parts of galaxies. All right, so stars are exponentially distributed in galaxies. Typical scale length is about 1/4 of R25. All right, now gas has a scale length of about half of R25, so that means that as you go out, you get increasingly gas-rich. So the gas fraction goes up as you go to the outer parts of galaxies. And if you just plug into these formulae, here is sort of what you predict for the metallicity as a function of galactocentric radius in the outer parts of galaxies. All right, in the inner parts, what you'll get depends on whether you're accreting or a closed box. But in the outer parts where the gas fraction is small or is very large, you get about the same thing, and you get a very steep gradient that more or less just follows the gas fraction. All right, and that's just because you get metal production that's just proportional to the tiny amount of the gas you've turned into stars. That's all. The problem is, you don't see anything like that. All right, if you look at what's actually seen outside of R25, and here's some data from Jeff's work, it's flat. All right, so if stuff just sits where it's made, if the metals just sit at the galactocentric radius where they're made, the gas just sits at the galactocentric radius where it's made, then you get unavoidably a very steep gradient in metallicity at large galactocentric radii, and that's exactly the opposite of what we observe. All right. We also observe that there's very little azimuthal variation. All right, and we'd like to explain that too. All right, so that's the problem that I want to address in this talk.
This observation, is this probing, because you measure this at H2 regions, and therefore you measure it exactly where you have star formation. If you'd actually average out the metallicity over all the gas, it's all forming stars, it would be much lower.
No, there doesn't seem to be any evidence of that. So first of all, I can say you can measure from H2 regions, but you can also use planetary nebulae, which are sort of not measuring the gas right where the stars are forming. It's measuring the gas around the white dwarfs that are forming planetary nebulae, and you don't get substantially different results. All right, so what I'd like to propose is that there's a simple solution, which is to remember that galactic disks are disks, and disks are accretion disks. All right, a disk is God's mechanism for separating mass and angular momentum. All right, that's what disks exist for. All right, they transport angular momentum out and mass in, and there's no reason that galactic disks don't do this, just like every other disk in the universe. All right, and so to have this transport, you need some form of turbulence, and the dominant source of turbulence in galactic disks, I'm going to argue, is just gravity. Galactic disks are self-gravitating. All right, so here's my cartoon. We have IgM accretion coming into large galactocentric radii. We have an inflow through the disk toward the bulge. All right, and the way the energy balance works here is that if you've got turbulence and you've got no source of energy input, the turbulence will invariably decay. That will lower your velocity dispersion. All right, and that, in turn, will push you towards gravitational instability. Your tumor Q will go down. All right, but tumor Q is a measure of stability against gravitational collapse. And if your tumor Q gets too small, then you'll get an instability, and that instability will transport mass inward, angular momentum outward. And when you move mass down the potential well, its gravitational potential energy gets more negative. Its kinetic energy, to conserve energy, has to go up. So that raises the velocity dispersion. All right, so that's how the energy balance in this system works. Your turbulence is decaying, you're losing energy to make that up, you move mass down the potential well, that drives turbulence and raises the velocity dispersion back up. Now, you can also have star formation feedback, and that can raise your tumor IQ as well, of course. All right, but that can't be that important at large galactocentric radii, just because there's so little star formation out there. All right, if I go out to like 2R25, where remember, there's tons of H1, right, I have tiny little dinky supernova remnants scattered in this vast disk of H1. All right, so it can't be the supernovae that are dominating out there. All right, so I'm going to argue that instead it's really gravity that's running the show. All right, so to try and convince you of that, I'm going to show you some simulations, and this is Nathan Goldbaum's work. So these are isolated galaxy simulations. All right, they were run at 20 parsec gas resolution, live stars and dark matter. And these simulations are sort of similar to some of the work that, for example, Florent Reynaud has done, that others have done. What I'd say is that this is sort of intermediate between the cosmological simulations and the local galaxy simulations, in that we don't have quite the resolution of the highest local galaxy simulations, but we're going to run significantly longer so that we can actually reach something like a steady state. All right, so we're going to run for 600 megayears. All right, our initial conditions are taken from the Agora isolated disk initial conditions. So these are Milky Way-like galaxies. We include photoelectric heating, cooling to less than 100 Kelvin. So we develop a realistic multi-phase ISM. We've got H2 region and supernova momentum feedback with a time delay. All right, and we can also do runs without feedback as a control to understand what's going on. And we'll try a range of gas fractions appropriate to the local universe, 10 to 30%. All right, so here's your reward for sitting through that. This is what one of these simulations actually looks like. All right, you can see that it collapses. It forms a flocculent spiral pattern. This is one of the simulations with feedback. So if you watch carefully, you'll see that whenever a region starts to collapse, it gets blown apart by the feedback. All right, and we run until we reach a statistical steady state. All right, now, what do we learn from these simulations? Well, we learn a few things. One, the disk stabilizes at a tumor Q of about 1. All right, and that's shown here. Here's Q gas in our low gas fraction, fiducial high gas fraction. Now, the important thing is this result is unchanged whether or not we include feedback. We can have no feedback whatsoever. The disk still goes to Q of 1. All right, the thing that makes galaxy disks have Q of 1 is not star formation feedback. It's gravity. Because if you try and go below Q of 1, you will drive turbulence that will drive mass inward, and that will raise the velocity dispersion. All right, so we get Q of 1 and a velocity dispersion of about 10 kilometers a second, independent of whether we include feedback or not. All right, so this has important implications. If your model for sort of what maintains Q of 1 involves star formation feedback, well, no, in fact, star formation feedback is not required to maintain Q of 1. It's not even helpful for maintaining Q of 1. What maintains Q of 1 is the same thing that happens with any instability. Instabilities tend to self-regulate into a marginally stable state. That's what every fluid instability does.
I don't see Q going to 1, I see Q going to 10.
So if you wait long enough, it does go higher, and the reason it goes higher is that we run out of gas in the simulations without feedback. These are the no feedback simulations, and so if you wait long enough, you'll run out of gas, and then Q will go up. In the simulations with feedback, we have a much lower star formation rate, and Q stays at 1. All right, so in fact, having feedback, ironically, doesn't raise Q, it lowers Q because it prevents you from running out of gas. All right, and we maintain this velocity dispersion of about 10 kilometers a second even without feedback. All right, so that's lesson number 1. Lesson number 2 is that we move mass around. All right, so let me walk you through this sort of somewhat complicated plot. All right, so the x-axis is radius, the y-axis is time. So at every radius and time, we can ask, what is the average mass flux through that region? And we colored it either red or blue, depending on whether the mass flux is inward or outward. All right, and so you can see initially we're dominated by sort of transients from our initial conditions, but after a while we reach this sort of fully turbulent state. And then we can ask, at each radius, if we average above this blue line when we've reached sort of fully saturated turbulence, what's the mean rate of mass transport? Because, of course, at times it's in, at times it's out. We want to know what the average is. And that's this. This is our mean mass transport rate. And the dashed line there is the cumulative star formation rate interior to that radius. And what I want you to notice is that these two are about the same. That is, the rate at which we're moving mass inward equals the rate of star formation. So we've got a solution to this problem. We can move mass inward by gravitational instability at the rate required to supply the star formation. So we've resolved the problem of how do we fuel the star formation. The answer is we move mass inward through the disk via gravitational instability. The metals get moved around too, and just to illustrate this, all right, we took one of these simulations and we just painted on a distribution of metals. And the natural way to do this, it turns out, is to paint them on with eigenfunctions, Fourier-Bessel functions. So here's a Fourier-Bessel mode we painted on. Here's another one we painted on. We let the simulation run for a little while, and we see what the distribution looks like. And then you can take the inner product of the initial and the final after you take out the overall rotation. And you can ask, how much have the metals been redistributed? And from that, you can derive a characteristic mixing time scale for the different modes. And that's what's shown here. Here's our mixing time scale. And what I want you to notice is that measured in years or in galactic periods, for all the non-axisymmetric modes, all the m greater than 0 modes, you completely mix out any metallicity gradient in about an orbit. For the axisymmetric modes, it takes, depending on the radial variation, takes a few orbits. Maybe as many as 10 as we go to the biggest modes. But this is a mechanism for flattening a metallicity gradient. This is a mechanism for redistributing the metals and for guaranteeing that there'll be no azimuthal variation. All right, so the same turbulence that's moving mass around is also moving metals around. All right, you can also move metals around with thermal instability. I'm going to skip this in the interest of time because I want to talk about how we can put this into a cosmological model. And this is John Forbes' work. All right, because we now have some rules. The rules are our disk asymptotes to Q of 1, and it holds itself there via gravitational instability. And if you know that, you can then make a very simple 1D code where you enforce that. Because I've got an alpha disk, but instead of the alpha describing my viscosity being arbitrary, I'm going to choose it to enforce that Q stays at 1. And then I can just run a simulation over a cosmological timescale. All right, and we put in stochastic IgM accretion, star formation, metal transport. We have this neat code that does this called the Gravitational Instability Dominated Galaxy Evolution Tool, or GIDGET. We're good at acronyms here. All right, so here's just an example of what one of these simulations looks like, and I just want to walk you through this diagram before I play the movie so you can understand it. What we're looking at here is the mass balance at different radii in the galaxy, and we have things that add mass and things that take away mass. Red is star formation and galactic winds, which take away mass. All right, mass can be transported either inward or outward by gravitational instability, and that's dark and light blue. And then we have cosmological accretion, which is orange. All right, and above and below the axis are things that add mass, things that remove mass. And what I want you to notice is that we've normalized things so that if the positive and negative terms are equal, then things stay in this band from minus 0.5 to 0.5. So, for example, at this snapshot, here, for example, cosmological accretion is balancing mass transport with star formation making a minor contribution. In here, inward gravitational instability and star formation are in nearly perfect balance. So mass is being moved inward by gravitational instability at a rate that equals the rate at which it's being consumed into star formation. Yes?
Is that log or absolute?
This is absolute, but it's been normalized to the absolute value so that between minus 0.5 and 0.5 corresponds to equilibrium. Up here, where it goes to 1, that means the mass adding terms completely dominate. All right? Down here would mean the mass removing terms completely dominate. All right, so at large galactocentric radii, the only thing that's going on is cosmological accretion, more or less, and you're not in equilibrium. All right, so this is a snapshot. Let's look at how a galaxy disk evolves from redshift 2 to today. All right, and what I want you to notice is that we have this region of equilibrium in much of the disk, where we're in equilibrium between mass transport, accretion, and star formation. All right, so galactic disks are more or less in equilibrium between these processes. All right, and that's what sets the distribution of gas. And we can look at the distribution of gas versus radius in the simulations, and here's what we get, and if we normalize it to the observations, lo and behold, we match. All right, and I'm going to skip the galactic center because I see the chairman standing up, and I'm done. I'll just put up this up. I thought about trying to dodge Piero, but decided against it. Even though he promised not to hug me, which was very kind.
I think it's really a key problem that you're addressing here. I just wonder, when the gas is flowing down, are you sure it's not forming stars in the process?
Oh, it is forming stars in the process.
So is it consistent with the fact that, as you said, you don't see that much star formation in the outer side of the Milky Way-like galaxies?
Oh, so at very large yeah. So if I go back to,
or let's say, the star formation distribution that we actually observe in the Milky Way with respect to what you would predict.
So we did in the paper compare sort of where the star formation was taking place to the observations, and it is a reasonably good match. Now, partly that's because we put in by hand that star formation follows H2, and we have a model for where the H2 is that is calibrated against observations. It's theoretically motivated, but it's also calibrated against observations. So yeah, I mean, out here at large galactocentric radii, there's almost no star formation. And as you go in, lo and behold, here's where star formation starts picking up, and that's where you start getting an appreciable fraction of H2 in your disk.
So you haven't mentioned the possible role of a galactic fountain and how it could provide some accretion, which is not directly cosmological, but actually triggered by the star formation itself through the feedback.
Yeah. So I didn't solely for reasons of time. So galactic fountains are certainly important, but if you actually look at the simulations that people who work on galactic fountains have done, you find that they tend to deposit their mass at radii that are fairly large. All right, where most of the mass tends to come in from a galactic fountain is not, where the star formation is taking place. It's a little bit further out. It's sort of 10 kiloparsecs for a Milky Way-like galaxy. So it has the exact same problem as the cosmological accretion, which is that where you're adding most of the mass is not where most of the star formation is. And that's partly just a matter of area, right? The star formation is taking place mostly in a fairly small, by area, region of the galaxy. And so if you just dump stuff randomly, even if you have no angular momentum preference, it'll mostly miss where the star formation is.
There is an additional process, which is interaction of the fountain.
Yeah. No, I'm referring specifically to those simulations. If you actually read their papers and ask, so I'm totally blanking on the guy's name from who's done the most work on this. If you read those papers, it mostly lands at 10 kiloparsecs. So That doesn't solve the problem. It gives you mass, it just gives it to you in the wrong place.
Okay, can I very quickly ask for a clarification? You made a strong statement on what feedback actually doesn't do rather than do. But, there is many forms of feedback, and I've learned they can be implemented in very many different ways. So how confident are you that your statement is robust towards all the possible variation in implementation, in physical terms?
Okay, so what I can say is in these simulations, we don't resolve this out of Taylor phase, and so we implement feedback as momentum feedback. All right, so we put in momentum feedback. That is more or less the same as what's going on in, for example, the fire simulations. What they're doing is mostly momentum feedback in their cosmological simulations. Feedback is really important for some things. It's really important for regulating the star formation rate. If we have no feedback, then our star formation rate is way too high and it disagrees with observations. All right, so we need feedback to get the right star formation rate. We just don't need it to maintain Q of 1. All right, and I think that's robust in the sense that we can turn the feedback off entirely and we still get Q of 1.
Yeah, do you have a sense of how a bar would shift the equilibrium that you're talking about?
Right, so that's the part of the talk I didn't get to give because I ran out of time. So what's going on with bars is you only get bars once you've started depleting the gas, right? You can't form a bar if the gas fraction is 20%. All right, people assume study bar formation, it's a phenomenon that occurs after you've depleted the gas. Okay. All right, so now what it can do is it can, after you've depleted the gas, give you a mechanism to dump gas to the very center of a galaxy. And in the part of the talk I didn't give, I would have explained how that very naturally gives you episodic burstiness at galactic centers, gives you molecular gas that's very turbulent. If you'd like, there's a paper, I'll just put up the reference and you can read the paper. So the reference is this paper by myself and Dietrich Kreysen, which was on AstroPH very recently, where we worked through the mechanics of that.
Okay, thank you very much, Mark. Next speaker is Pablo Perez Gonzalez. Star formation,
Yeah,
the role of mass transport within galaxies.
All right, thank you. I see people are settling back in with their coffee. All right, so I am going to talk about how stuff in galaxies gets arranged. All right, so I know this is a mostly cosmology meeting, and at cosmology meetings, galaxies are often approximated as, it's not a cosmology meeting, Sandy's shaking her head at me, it's a galaxies meeting. It's an extra, it all looks the same to me. Remember, I started my career working on things that are, less than a kiloparsec away. All right, so it's far. And people who think about far tend to regard galaxies as points. So the theme of this class, inside about half of R25, so inside here is molecular. Most of the gas further out is H1. All right, so there seems to be this fairly universal profile. The scale length is about half of R25. And again, inside half of R25, most of the gas is molecular. Outside, it's not. We'll see a few galaxies, including our own Milky Way, have central dips, have a gas surface density distribution that goes down in the center. That's a sort of 10% effect. About 10% of the population has a central hole for L-star galaxies today. The other thing I want you to notice is that the H1 distribution is extremely extended. All right, this plot stops at 20 kpc, but in fact you can detect it significantly further out. You can routinely detect 21 centimeter emission 30 kpc from the center of a galaxy. All right, so the H1 disks of galaxies are very extended compared to their stellar disks. And as you go further and further out, you just get more and more gas rich. All right, so how about the star formation? How's that arranged? Well, we've heard this several times. In the centers of galaxies, the H2 depletion time is roughly constant. It's a few gig years. All right, and star formation just sort of follows H2. All right, so what that means is that since most of the H2 is inside half of R25, that's where most of the star formation is too. All right, the star formation distribution more or less just follows the H2 distribution. All right, so star formation is more centrally concentrated than total gas because it's following the H2 and not the H1, which is, then I'll talk about how stuff gets moved around in galaxies, and I'll focus on, in galactic disks, the transport of mass and metals. I'll talk a little bit about what happens at the very centers of galaxies, and then I will summarize for those who have fallen asleep. All right, so, slight lag there. Let's talk about, well, how is gas arranged in galaxies in the local universe? So in disks in the local universe, turns out gas is distributed in an approximately exponential distribution. All right, so here's total gas surface density versus radius, and you can normalize things to R25, and you see you wind up with this fairly universal exponential profile. All right, now, most of the gas talk is that galaxies are not in fact points, and we should maybe pay a little bit of attention to that. All right, I should mention, most of the work I'm going to show is not my own. It is the work of others, and in particular, 3 graduate students, 2 of whom are probably known to most of you. Nathan Goldbaum, who just recently defended, hooray. John, who you heard from earlier in the week, and Antoine Petit, who is a visiting student from France here a few years ago. All right, so here's the outline of the talk. So I want to start with what we know about the radial distribution of gas star formation in metals and galaxies in the local universe, because that's really the thing I want to focus on trying to make sense of. How did galaxies get into their current shapes?